Hello again. Now that we understand plane mirrors, let's turn our attention to spherical mirrors. Now, spherical mirrors are mirrors which are cut out from a sphere. So let's first draw a sphere. Let's say this is a sphere made of glass. The radius of this sphere R is called the radius of curvature. So R is the radius of curvature. And the center of the sphere C is called the center of curvature. Now, as long as nothing is polished, this is not a mirror, this is a glass. Now, what we'll do is, we'll cut a part of this glass, the spherical glass. And after doing that, we polish its outer surface. So let's draw it again on this side. So if a part of the mirror is cut out and the outer side is polished, then the mirror that you get is called a concave mirror. So how do you identify a concave mirror? The center of curvature for a concave mirror, which will be somewhere here, is on the side which is reflecting. So please note that even though we've cut this out of a sphere, this is still a part of a sphere, right? Though the rest of it is not there, this is still a part of this sphere. And the center of this sphere is called the center of curvature, and its radius will be called the radius of curvature. So, for a concave mirror, the center of curvature is the center of the sphere of which this mirror is a part, and radius of curvature is the radius of the sphere of which this mirror is a part. Right. So to obtain center of curvature or radius of curvature, we can complete the sphere and then see where the center lies and what the radius of that sphere is. Though usually the information of the radius of curvature is given to us. Now, if the same thing was done, that is, a part of this mirror was removed, but instead of polishing the outer surface, if we polish the inner surface, which is this, if we polish this inner surface, then the mirror that we get is called a convex mirror. So this mirror is a convex mirror. Once again, we can define the center of curvature and the radius of curvature for this mirror. The center of curvature is the center of the sphere of which this mirror is a part. And radius of curvature is again the radius of the sphere of which this mirror is a part. Now, we will look at how light reflects on these surfaces. Before we discuss that, let me mention that the laws of reflection that we had discussed for a plane mirror hold for spherical mirrors as well. In fact, those laws of reflection hold for every reflection. If you recall, the laws of reflection stated that first, that angle of incidence is equal to the angle of reflection, and second, that the incident ray, the reflected ray, and the normal all lie in the same plane. Let's now look at the relation between the object distance and the image distance for a spherical mirror. So let's now discuss reflection of a curved surface. So let's take a concave mirror to explain all the related terms. So first of all, the line on which the object lies is called the principal axis. So now, principal axis is a line from the object to the mirror such that this line is normal to the mirror. So on the principal axis, first thing, the object lies, and secondly, it is normal to the mirror, which means that this line close to the surface of the mirror is perpendicular to it. So at this point, it would be perpendicular to the mirror. Right. Now, the point where the principal axis touches the mirror is called the pole. So the pole is the point of intersection of principal axis with the mirror. So pole, let me write, is the point of intersection. Point of intersection of principal axis. This PA is short form for principal axis. So this is the point of intersection of principal axis with mirror. Now, there is an important property of pole that we must remember, and that is that all distances are measured from pole. So, the pole, which is the point of intersection of principal axis and the mirror, is the point from where we will measure all distances. So what distances are we talking about? The image distance, the object distance, and the radius of curvature. So in this case, the center of curvature could lie at this point. The center of curvature, if you recall, is the center of the sphere of which this mirror is a part. So if I was to complete the sphere of which this mirror could be a part, although this does not look like a sphere, this is supposed to be a sphere, and so somewhere here would be the center of curvature. So this point C is the center of curvature of this mirror, which is basically the center of the sphere of which this mirror is a part. And the distance of center of curvature to the pole would be the radius of curvature, because radius of curvature is the radius of the sphere of which this mirror is a part. Right. Now that we know about principal axis and the pole, let us look at some of the properties for reflection. So, if this is a mirror and this is its polished side, let's represent the object by this arrow. So this is an object with some height. The first property of reflection is that any line which is parallel to the principal axis passes through a point which is called the focus. So F here denotes focus. So focus is a point from where any ray which is parallel to principal axis after reflection will pass. So if I was to draw multiple rays, then all of those rays which are parallel to the axis would finally pass through the focus. And in case of mirrors, the focal length is equal to half the radius of curvature. So focal length I have denoted by the small f. So let's first ask, what is focal length? the focal length is the distance between the pole and the focus. You recall that all distances are to be measured from pole. So, we measured the distance of focus from the pole and we've named it as the focal length. Right. So, first property is that any line which is parallel to principal axis passes through focus. Right. The second property is that any ray which comes direct to the pole is reflected at an equal angle. This is the direction of the incident ray, then this is the reflected ray. Let me draw this again. So if this is the mirror and this is your object, then a ray starting from this point and reaching the pole will be reflected at an equal angle back to where it came from. This is because if you think about it, this principal axis is actually the normal at this point, and hence this angle is basically the angle of incidence, and hence this is the angle of reflection. If you recall, I told you that the laws of reflection hold for spherical mirrors as well. And so, any ray which comes to the pole is reflected at an equal angle back in that direction. Right. So, these are the two laws that we will use to create images. There's a third law which is actually a converse of this law, which says that if a ray passes through the focus, then after reflection it becomes parallel to the principal axis. This is fairly obvious, right? So if a ray, when it is incident parallel to the principal axis, reflects through the focus, then any ray which comes through the focus must become parallel to principal axis. Right. So these are the three laws that are used to obtain images in case of a spherical mirror. Now, though we have used these laws for concave mirror, they hold equally well for a convex mirror. Now, we will try to derive the expression which relates the object distance and the image distance. But we will do that in the next session. So in this session, we learned about spherical mirrors. We learned that spherical mirrors are made by cutting out a piece of a sphere. The radius of the sphere of which this piece is cut is called the radius of curvature of that mirror. And the center of the sphere of which the mirror has been cut out is called the center of curvature, the radius of curvature of that mirror. And we saw that a mirror has a focal length which is equal to half the radius of curvature. Then we saw three principles which are used to obtain images. The first is that any ray which is parallel to principal axis will pass through the focus after reflection. The second principle is that any ray which is directly incident on the pole is reflected back at the same angle at which it was incident. And the third principle is that any ray which passes through the focus will become parallel to principal axis after reflection. Now, one last thing. The focus has a special significance. You recall that every ray which is parallel to the principal axis finally passes through the focus. So let's look at this animation which shows a lot of rays coming parallel to principal axis. You see, all of them are concentrated at the focus. Now, whenever the light source is at a great distance, the light rays coming from that source become nearly parallel to the principal axis. As a result, if you use a mirror, all the light that is falling on a mirror, a concave mirror, gets concentrated on the focus. So this property of concave mirror is used for heating purposes. We will discuss these things again in detail next time when we derive an expression which relates the image distance and the object distance. Thank you.